So the exam is a week from Wednesday, March 24th, and there'll be a review sheet that I'll go over on Monday, which is, I guess, the 22nd. So let's recall that we have a positive integer m and integers a and b, and we say a is congruent to b mod m. This is the basic relationship. If m divides a minus b, that is, a minus b is m times q for some integer q. And we prove that congruence is an equivalence relation. That means it's reflexive. Every number is congruent to itself mod m. It's symmetric. If a is congruent to b mod m, that implies b is congruent to a mod m. And it's transitive. So if a is congruent to b mod m and b is congruent to c mod m, these two statements imply a is congruent to c mod m. And for every integer a, the congruence class of a mod m is the set of all integers of the form a plus mq. Q is an integer. So we write this as a plus mz. So this is the set of all numbers, all integers that are congruent to a mod m. And a complete set of representatives, there are many such, but one example of a complete set of representatives of the congruence classes is the set of numbers, the non-negative integers from 0 to m minus 1. This means that for every integer n, there is a unique integer a in this set such that n is congruent to a mod m. So we have a partition of z into congruence classes. mz, 1 plus mz, mz is just 0 plus mz, 2 plus mz, and so forth. And we write z mod mz. This is the set of congruence classes modulo m. So this is a finite set. This is a set with exactly m elements. Each element is a congruence class. So the set of integers is infinite, but we're dividing this infinite set up into a finite number m of pieces for the different congruence classes. We can add and multiply congruences. So this was a very important algebraic fact. If A1 is congruent to A2 mod m, and B1 is congruent to B2 mod M, then you can add the congruences. A1 plus B1 is congruent to A2 plus B2 mod M, and you can multiply them. A1 times B1 is congruent to A2 times B2 mod M. So this is a basic fact, and you need to be able to prove it. For example, A1 congruent to A2 mod M means that A1 minus A2 is, say, M times Q. And B1 congruent to B2 mod M implies that B1 minus B2 is M times, let's say, R. So if you look at A1 B1 minus A2 B2, we have to show that's divisible by M. I can write this as A1 B1 minus A2 B1 plus A2 B1 minus A2 B2, because this is just 0. I've just added 0. This is A1 minus A2 times B1. This is A2 times B1 minus B2. A1 minus A2 is MQ. B1 minus B2 is MR. So this is M times the integer QB1 plus A2R. So A1 B1 minus A2 B2 is a multiple of M. So A1 B1 is congruent to A2 B2 mod M. So that's a nice piece of elementary high school algebra, but it's very important. This also tells us that we can define addition and multiplication of congruences. So therefore, we can define addition and multiplication of congruence classes. So suppose that X and Y are congruence classes in Z mod MZ. So X is, let's say, A1 plus MZ for some integer A1, and Y is B1 plus MZ for some integer B1. But this integer A1 isn't unique. Suppose for some other integer, it's the same congruence class A2 plus MZ. And suppose for another integer B2, this is the same as the congruence class B2 plus MZ. So because A1 plus B1 is congruent to A2 plus B2 mod M, right? That's the fact I just stated. We can define the sum of the congruence classes to be the congruence class of A1 plus B1 plus MZ. And that's unambiguous because this is the same as the congruence class A2 plus B2 plus MZ, because these two numbers are congruent, so they lie in the same congruence class. So this is a well-defined addition of congruence classes. And we can define the product of two congruence classes, take these representatives, A1 and B1, and just multiply them. So this is well-defined. There's no ambiguity. It does not depend on which representative of the congruence class you pick. And remember, we defined a ring in algebra, a ring is a set R with two operations, addition and multiplication, that satisfies the following properties. First, with respect to addition, R is an additive abelian group. Second, let me call this 0, 1. Multiplication is associative. Right? X, Y, Z is X, Y, Z for any X, Y, and Z in the ring. There exists an element 1 in the ring. We just call it 1. You can call it anything you like. Such that, which is a multiplicative identity, X times 1 and 1 times X is equal to X for all X. We don't assume that there's the multiplicative inverse, but we do assume that the distributive law is satisfied. X times Y plus Z is XY plus XZ. And also in the opposite direction, Y plus Z times X is YX plus ZX. So any set with an addition and multiplication that satisfies these three properties is called a ring. And R is called a commutative ring if the multiplication is commutative, XY equals YX. So Z, the integers with the usual addition and multiplication, is a ring. So is the set of rational numbers, the set of real numbers, the set of complex numbers. These are infinite rings. And what's very important for us, the set of congruence classes mod M is also a ring. These are infinite commutative rings. And this is a finite commutative ring. So groups and rings are two of the basic structures in algebra. And these you know from birth, basically. And this is the new one, perhaps. The set of congruence classes modulo M is always a commutative ring. Now, there's a difference between the ring Z and the ring Q. Namely, in Z, the element 2 has no multiplicative inverse. So just to be careful about the language, let us make the following definition, that R be a ring. The element U in the ring is called a unit if there exists a V in the ring such that U times V and V times U is the multiplicative identity. So U is a unit if U is invertible, has an inverse. And the V we would write as U minus 1. But not every element has an inverse. Not every element is a unit. So in Z, 2 has no multiplicative inverse. 2 is not a unit because there's no integer n such that 2 times n is 1. In the rationals, 2 is a unit. If U is 2, U inverse is a half, right? 2 times a half, and a half times 2 is 1. So in the rationals, 2 is a unit, but in the integers, 2 is not a unit. Okay. Any questions about this? This is terminology, but it's very important.
Can you please repeat?
Yes? So
Can you
you
please?
have a ring, and an element in a ring is called a unit if there's another element V, which is the multiplicative inverse. So U is a unit if there exists a V such that UV and VU equals 1. So in the rationals, U equal 2 is a unit because if you take V equal to a half, which is also a rational number, U times V and V times U, this is 2 times a half or a half times 2, equal to 1. But a half is not an integer. So in the ring of integers, 2 is not a unit. But in the ring of rational numbers, 2 is a unit. You know, whenever you talk about something being a unit in a ring, it depends on the ring. So let R be a commutative ring. So you can add and multiply. Let R, this is a times sign, be the set of all units in R. So this is not empty. First of all, 1 in R, the multiplicative identity, is a unit because 1 times 1 is 1. So the inverse of 1 is 1. So 1 is always an element in the set of units. And it's a very important algebraic fact that the set of units is a multiplicative group. So this means that this set is closed under multiplication, contains the identity, and contains the inverse of each element. Of course, it's obviously abelian because multiplication in R is commutative, so multiplication in R star is commutative. So how do we know it's a group? So suppose U1 and U2 are units. Then they have inverses. So there exist elements V1 and V2 in the ring such that U1, V1, and V1, U1 equals 1. And actually, I don't even need to, 1, well, and U2, V2 equals 1. So suppose I multiply U1 and U2, and I multiply V2 and V1, I multiply and I look at this product. So by associativity, this is U1 times U2, V2 times V1. This is 1. So this is just U1, V1, which is 1. So U1, U2 has inverse V1 or V2, V1. So U1, U2 is a unit. So it's in the set of units. So this set is closed under multiplication. And 1 equal 1 times 1 is a unit. 1 is a unit. I just said that already. And if UV equals 1, then V is also a unit. with inverse equal to u, right? U times v is 1. So again, it's quick to say all this, but at home, going over the lectures and studying the text, you really need to understand all of the arguments and what's going on. It takes a lot of paper and pencil time to work everything through. So in every ring R, there is the group of units R times. Notice 1 times x and x times, 0 times x and x times 0 is 0 for all x, which means it's not 1. So 0 is never a unit. So the group of units is contained in R with the 0 element removed. And we say that a commutative ring R is a field. So this is the next definition. If every non-zero element is invertible, which means is a unit. So R is a field if and only if the group of units is everything in R except 0. If you take the integers, what is the group of units? Well, 1 is always a unit, and -1 is a unit, and these are the only ones. These are the only integers that are invertible. Because if you take a number, an absolute value bigger than 1, the inverse isn't an integer. So Z is certainly not a field. But if you take the rational numbers, if you take A over B different from 0, x is equal to A over B, then A over B times B over A is 1. So this has an inverse B over A for every non-zero rational. So the rational numbers, this is a field. So some commutative rings are fields and some are not. So what about our ring of congruence classes? Is the ring of congruence classes C mod MZ a field? And the answer to the question is sometimes yes, sometimes no. For example, suppose we take m equal to 3. So we're looking at Z mod 3Z. And this has 3 congruence classes. So I'm going to write, just for simplicity, if I take the congruence class A plus 3Z, I'm just going to write that as A bar, so I don't have to keep writing all this. So you have the congruence class of 0, the congruence class of 1, and the congruence class of 2. So the congruence class of 1 multiplied by itself is the congruence class of 1 times 1, or 1. So in any case, this is a unit. This is the group of units. What if you multiply 2 by itself? You get 4. But mod 3, 4 is congruent to 1. So the inverse of 2 is 2. This is also a unit. The 3 congruence classes, the 3 elements in this ring, the 2 non-zero elements are units. So Z mod 3Z is a field. Okay. Suppose I take M equal 4, and so I'm looking at the congruence classes modulo 4. So again, I'm going to write the congruence class of A plus 4Z is A bar. So this consists of the congruence class of 0, 1, 2, and 3. So I claim the congruence class of 2 is not a unit. Why is that? Well, suppose there's a congruence class X bar, so 2 times X is 1. What does this mean? This means the congruence class of 2 is the congruence class of 1. This means 2x is congruent to 1 mod 4. That means 2x minus 1 is 4 times y, which means 1 is 2x minus 4y is even, which is not true. It's a contradiction. So this congruence class is not 0, but it's also not a unit. So Z mod MZ is not a field. So you might take a look at this argument for a minute or two.
Can you explain again?
Okay. So let me just do it from scratch. So we let R be the congruence classes mod 4. So let's say X is a unit in this ring if there is a congruence class Y bar in that same ring such that X times Y is 1. Right? Now, X means X plus 4Z. This is all X prime, all integers X prime, where X prime is congruent to X mod 4. That's what a congruence class is. And the congruence class of X times the congruence class of Y is the congruence class of XY. And that's the same as the congruence class of 1. That means that X, Y, and 1 are congruent mod 4. So I claim the congruence class of 2 is not a unit in this ring of congruence classes mod 4. If 2 bar is a unit, then there exists a congruence class Y such that the class of 2 times the class of Y is the class of 1, which is the same as saying 2y is congruent to 1 mod 4, which is the same as saying 2y minus 1 is some multiple of 4, which means 1, if I just rearrange this equation, is 2y minus 4z is 2 times y minus 2z, which is false. plus 2 doesn't divide 1. So therefore, the congruence class of 2 is not a unit of mod 4. So that's the argument. Now, the question I started by asking is the ring of congruence classes Z mod MZ a field? And my answer was sometimes yes, sometimes no. So when M is 3, the answer is yes. When M is 4, the answer is no. And we would like to know exactly for which integers M, Z mod MZ is a field. Because fields are very nice. Once you can add, subtract, multiply, you have a ring. But if you can add, subtract, multiply, and divide, then you have a field, and you can do a lot more algebra. So to solve that problem, we have to consider, or we shall consider, linear congruences. So in the lecture last Wednesday, a linear congruence is a congruence of the form AX congruent to B mod M. And we want to know when can we solve this and how many solutions there are. So we want to know when can we solve. This is like an equation, but it's not an equation, it's a congruence, because it's not that AX equals B. It's that AX is congruent to B mod M. The modulus M is a positive integer, A and B are integers, and we want to know when there exists a solution. So the big theorem that I proved last week says AX is congruent to B mod M has a solution if and only if B is divisible by, that's the same as being B is congruent to 0, modulo the greatest common divisor of A and M. So the proof. So if AX is congruent to B mod M, if this has a solution, that means that AX minus B is M times Y. Or if I rearrange that, B is AX minus MY, which means that if D divides A and D divides M, then D divides B. So the greatest common divisor of A and M divides B. I mean, if A is DQ and M is DQ prime, then B, which is AX minus MY, is DQX minus DQ prime Y, is D times QX minus Q prime Y, D divides B. So any common divisor of A and M divides B, and particularly the greatest common divisor does. So B is congruent to 0, modulo the greatest common divisor of A and M. So that's the proof of half of the theorem. This says that if AX is congruent to B mod M, then B is congruent to 0 modulo this greatest common divisor. So that's the proof going from left to right. And what about a proof in the opposite order? So using the Euclidean algorithm, or in other ways as well. Suppose we let D be the greatest common divisor of A and M. We know you can write this as a linear combination with integer coefficients of A and M. If D divides B, so B is equal to D times Q, well, if B is D times Q, multiply this equation by Q. We get B is DQ is AX plus MY times Q. Maybe I shouldn't call this X0 and Y0. So this is A X0Q plus M Y0Q. This is equal to B. So if I call this X, this says that B minus AX is a multiple of M. So AX is congruent to B mod M has a solution. So that's the second half of the proof. So if D is the greatest common divisor of A and M, we know we can write D as this integral linear combination of A and M. That is, there exist integers x0 and y0, so AX0 plus MY0 is equal to D. If D divides B, that means B is D times some quotient Q. You write D in this form and distribute. Call this number X. You have AX is congruent to B mod M. And we have several important consequences of this. So again, the theorem says AX congruent to B mod M is solvable. There exists an X which solves that congruence if and only if B is congruent to 0 modulo the greatest common divisor of A and M. So if the greatest common divisor of A and M is 1, if A and M are relatively prime, then every B is congruent to 0 mod 1. This just says 1 divides B, which is always true. So AX congruent to B mod M always has a solution for all B. If A and M are relatively prime, there's always a solution of this mod M. And in fact, the solution is unique mod M. Because if, let's say, AX1 is congruent to B mod M, and AX2 is congruent to B mod M, then by transitivity, AX1 is congruent to B, B is congruent to AX2, AX1 is congruent to AX2 mod M, which means the difference, AX1 minus AX2, is some multiple of M. If I factor A out, A, this is A times X1 minus X2. So we see that M divides A times X1 minus X2, and M is relatively prime to A. So by Euclid's lemma, M divides X1 minus X2, which means X1 is congruent to X2 mod M. So if you have two solutions of this congruence, X1 is congruent to X2 mod M. And conversely, if AX1 is congruent to B mod M, and X1 is congruent to X2 mod M, then AX1 congruent to AX2 is congruent to B mod M. So in the special case of a linear congruence, this is always my linear congruence. If A and M are relatively prime, this congruence has a solution for every B, and the solution consists of a single congruence class of integers. And there's a very special case of that. If A and M are relatively prime, then AX congruent to 1 mod M has a unique solution modulo M. A and M are relatively prime, there's a unique solution. Now, let's go back to our problem for which M is this ring of congruence classes a field. So A plus MZ is a unit in Z mod MZ, precisely when there exists a congruence class X plus MZ such that A plus MZ times X plus MZ is 1 plus MZ. But the product of these congruence classes is AX plus MZ equals 1 plus MZ, which is the same as saying AX is congruent to 1 mod M. And this has a solution if and only if this number 1 is congruent to 0 modulo the greatest common divisor of A and M. But the only positive divisor of 1 is 1. So if and only if A and M are relatively prime. Wow. So this is really a fantastic statement. What this says is the group of units in Z mod MZ is the set of all congruence classes A plus MZ where A and M are relatively prime. And we can choose for our representatives of the congruence classes just the integers from 0 to M minus 1. So this is all integers A from 0 up to M minus 1. So this is what the ring of congruent, the group of units is. And the number of elements in this When you put vertical lines around a set, that means the cardinality or the size of the set is the number of non-negative integers up to m minus 1 that are relatively prime to m, which is exactly phi of m. This is the definition of the Euler phi function that I defined last week. And we want to know when is Z mod mz a field? Z mod mz is a field if and only if the group of units is all the non-zero congruence classes. So a plus mz for all a from 1 up to m, which means the greatest common divisor of a and m is 1 for all a going from 1 up to m minus 1. And when does this happen? Well, if m equal p is prime, then all the numbers from 1 to p minus 1 are relatively prime to p. If a is between 1 and p minus 1, it can't be divisible by p. It's not big enough. But if m is composite, so d and q are both strictly between 1 and m, these are proper divisors, then the greatest common divisor of d and m is bigger than 1. So there's at least one congruence class in Z mod mz, which is non-zero and not a unit. So what we just proved is Z mod pz is a field for every prime p, and Z mod mz is not a field for every composite integer m. So let's look at an example. Let's say we take p equal to 5. So for each congruence class A, I want to find A inverse mod m, mod 5. So mod 5, there are 4 non-zero congruence classes, 1, 2, 3, and 4. What are the inverses? Well, the inverse of 1 is 1. 1 times 1 is congruent to 1 mod 5. What's the inverse of 2? Well, try 3. 2 times 3 is 6, is congruent to 1 mod 5. So if 2 times 3 is 1, 3 times 2 is also 1. It's the same calculation. What's the inverse of 4? I claim it's 4. Plus 4 times 4 is 16. 16 minus 1 is 15, which is divisible by 5. 16 is congruent to 1 mod 5. So in the field Z mod 5Z, the inverse of the congruence class 2 plus 5Z is 3 plus 5Z, right? That's what this says. So just so you get a little practice at this, suppose I let p equal 7, And for each non-zero congruence class mod 7, there's 6 of them, namely 1, 2, 3, 4, 5, and 6. Compute the inverses mod 7. So for each of these numbers, you want to solve AX congruent to 1 mod 7. So like when A is 1, X is 1. Right? What about 2? Solve 2X congruent to 1 mod 7. And 3X congruent to 1 mod 7, and so forth. So solve all of these congruences and fill in this table. Right? So you should spend a couple of minutes working this out. So for example, what's the inverse of 2 mod 7? What do you multiply 2 by to get something congruent to 1 mod 7?
Three.
Well, 2 times 3 is what?
6.
6. And is 6 minus 1 divisible by 7?
No.
No, so it can't be 3.
Four,
Well, what's 2 times 4?
8,
Is 8 minus 1 divisible by 7?
yes.
Yes. Then you are the winner. 4, because 2 times 4 is 8, is congruent to 1 mod 7. What's the inverse of 3? Mod 7. So you want to solve the congruence, 3x congruent to 1 mod 7. Well,
5,
okay, well, what's 3 times 5?
15,
And is 15 congruent to 1 mod 7? 15 minus 1 is what?
14,
14 divisible by 7?
yes,
So the answer is 3. So the inverse of 3, the inverse of 3 is 5. What's the inverse of 4? Well, we basically have it, because if 2 times 4 is 1, 4 times 2 is 1. And what's the inverse of 5? Well, it's 3, because 3 times 5 is 1, so 5 times 3 is 1. What's the inverse of 6? Mod 7. Well, what's the result? I mean, you just have to start multiplying a few numbers. 6 times 1, 6 times 2, 6 times
6.
3. Sorry, what is it?
6.
6. Because 6 times 6 is 36. 36 minus 1 is 35, is divisible by 7. So 6. So for each of the non-zero congruence classes mod 7, 1 to 6, here are their inverses. You'll notice there's some permutation of 1 through 6. It's just some rearrangement of those numbers. Okay, any questions about this? All right, there's one more important theorem about congruences I want to prove, which is something which is called the Chinese remainder theorem. And we're interested in when we can solve two congruences simultaneously to different moduli. So we're interested in finding one number x, where x is congruent to a mod m, and the same x is congruent to b mod n. And we want to know, when can we solve? It's like two equations that you have to solve. And sometimes there's no solution. Like suppose you want to solve x congruent to 1 mod 6 and x congruent to 2 mod 8. I claim this is impossible because if x is congruent to 1 mod 6, that means x is 1 plus 6 times y. And if x is congruent to 2 mod 8, that means x is equal to 2 plus 8z. So you would have 1 plus 6y equals 2 plus 8z, or 1 is 2 plus 8z minus 6y. This number is even and 1 is odd, so this is impossible. Right? So if you wanted to find a number that is congruent to 1 mod 6 and 2 mod 8, the answer is don't even waste your time trying. Here's a proof. There's no solution. Right? So this is not always possible. See, suppose I had x congruent to 1 mod 6 and x congruent to 3 mod 8. Can I solve that? Well, again, if x is 1 mod 6, that means x is 1 plus 6y. If x is also 3 mod 8, that means x is equal to 3 plus 8z. So if there's going to be a solution, then 1 plus 6y equals 3 plus 8z. That's the same as 6y equals 2 plus 8z. Subtracting 1. So if I divide by 2, this says 3y is 1 plus 4z. I guess if I took z equal minus 1, this would be minus 3. And if I let y equal minus 1, this would be minus 3. So that would be a solution when y is -1 and z is -1. So if I let x equal 1 plus 6y, that's 1 minus 6 is -5. If I plug in the same thing, 3 plus 8z is 3 minus 8 is also -5. So it looks like x equal -5 is a solution, right? Because -5 minus 1 is -6, is divisible by 6. -5 minus 3 is -8, is also divisible. So this pair of congruences does have a solution. This pair does not. If you wanted a positive solution, you could try x equal to 43. See, 43 minus 1 is 42, is 6 times 7. 43 minus 3 is 40, is 8 times 5. So here are at least two different solutions for this system of congruences. So this example, these two examples show us that sometimes a pair of congruences have a solution and sometimes they don't. And the Chinese remainder theorem gives us a necessary and sufficient condition for this set of congruences to have a solution. And what the Chinese remainder theorem says is exactly the following. The system of congruence is AX congruent, X congruent to A mod M, and X also congruent to B mod N, has a solution if and only if A minus B, if and only if A is congruent to B, modulo the greatest common divisor of M and N. So let's see here. Why did this fail? 6 and 8, the greatest common divisor of 6 and 8 is 2. And 1 is not congruent to 2, mod 2. But in this case, we had the same moduli, 6 and 8, with the same greatest common divisor, and 1 is congruent to 3, mod 2. So this system of congruences satisfied the condition, and this did not, and this one did. So this system had no solution, and this one had a solution. So let's see, proof. X is congruent to A mod M means X is an integer of the form A plus M times Y for some Y. And X is congruent to B mod M. If X is also a solution of the first congruence, that means A plus MY is congruent to B mod N, which is the same as saying MY is congruent to B minus A mod N. And this is a linear congruence. So this has a solution if and only if B minus A is congruent to 0 modulo the greatest common divisor of M and N, which is the same as saying A is congruent to B modulo the greatest common divisor of M and N. So this pair of congruences has a simultaneous solution if and only if this linear congruence has a solution, if and only if this condition is satisfied. So that's pretty good. Now, suppose this condition is satisfied and we want to find all solutions. Let's see, well, maybe before I do that, let's work another example. Suppose I have the system x congruent to 3 mod 7 and x congruent to 5 mod 9. So if you compare this to this notation above, A is 3, B is 5, M is 7, N is 9. The greatest common divisor of M and N is the greatest common divisor of 7 and 9, which is 1. So 1 certainly divides everything. So this pair of congruences will have a solution. So first, if x is 3 mod 7, x is 3 plus 7y for some y, and we want that to be congruent to 5 mod 9, which means we want to solve the congruence 7y congruent to 2 mod 9. And then you have to look for a solution. Notice 7 times minus 1 is congruent to 2 mod 9, because minus 7 minus 2 is divisible by 9. So you can take y equal minus 1, and x is 3 plus 7y, is 3 minus 7 is minus 4. So x equal minus 4 is a solution. Minus 4 is congruent to 3 mod 7, and minus 4 is congruent to 5 mod 9. Because 7 divides 7 and 9 divides 9. So for this pair of congruences, minus 4 is the solution. So spend a couple of minutes just looking at the details, just the arithmetic, to see that it works and why it works. Let me prove one more result connected with the Chinese remainder theorem, and then we'll do some more examples. So recall the greatest common divisor of two integers a and m, a and b, is the largest integer d such that d divides a and d divides b. So for example, the greatest common divisor of 6 and 10 is 2. 2 divides both those numbers and no larger integer does. The least common multiple of a and b is the smallest integer m such that a divides m and b divides m. So for 6 and 10, both of these numbers divide 60. So 60 is a common multiple. We denote the least common multiple by square brackets around the numbers. But 30 is a smaller number that's divisible by both 6 and 10. And 30 is the least common multiple. And it's a theorem, which is that for all positive integers a and b, the product of a times b is the product of the greatest common divisor times the least common multiple. And I'll prove that in a bit, but I'm going to use that to finish our discussion of the Chinese remainder theorem. Suppose, so if we have two solutions, ax1 congruent to b, or if ax is congruent to b mod m, sorry, x congruent to a mod m and x congruent to b mod m. So that x be a solution of this pair of congruences. Then x1 is congruent to a mod m, and x1 is also congruent to b mod n. This is another solution. If and only if x is congruent to x1 modulo the least common multiple of m and n. So we know this has a solution if and only if a is congruent to b modulo the GCD of m and n. And if that is the case, then all solutions lie in a particular congruence class modulo this least common multiple. So let's look at the proof. If x is congruent to a mod m and x is congruent to b mod n, and also x1 is congruent to a mod m and x1 is congruent to b mod n, then x is congruent to a and a is congruent to x1. X is congruent to x1 mod m, x is congruent to x2 mod n. This means that m divides x minus x1 and n divides x minus x1. So x minus x1 is a common multiple of m and n. And if a number is a common multiple of two integers, it itself is a multiple of the least common multiple. So x minus x1 is a multiple of the least common multiple of m and n. So x is congruent to x1 modulo this least common multiple. So just as the greatest common divisor of two integers has the property that it divides every common divisor of the integers, the least common multiple of two integers has the property that it divides every common multiple. So every common divisor divides the greatest common divisor, and every common multiple is divisible by the least common multiple. That's why this is true. So here's a problem. Find all solutions of the system of congruences x congruent to 5 mod 6 and x congruent to 8 mod 15. So notice that the greatest common divisor of the moduli 8 of 6 and 15 is 3, and 3 divides 8 minus 5. That is, 8 is congruent to 5 mod greatest common divisor of 6 and 15. So therefore, the system of congruences has a solution. What's the least common multiple of 6 and 15? Well, let's see. Someone should be able to tell me that. What's the smallest integer divisible by both 6 and 15?
30.
30. So the set of all solutions of the system of congruences is exactly one congruence class mod 30. So once you find one solution, you can find all solutions. And how do we find one solution? Well, if x is congruent to 5 mod 6, then x is 5 plus 6 times y for some integer y. And that has to be also congruent to 8 mod 15. So 6y is going to be congruent to 3 mod 15. So what's the solution of that? Well, I want to make it easier. If I have these three numbers divisible by 3, it's the same as solving 2y congruent to 1 mod 5. So I can take any y congruent to 3 mod 5. Plus 2 times 3 is 6, 6 minus 1 is 5. So I can let y be any number of the form 3 plus 5t, and then x which is 5 plus 6y, is 5 plus 6. Y is 3 plus 5t. This is 5 plus 18 plus 30t. This is 23 plus 30t. So any x congruent to 23 mod 30 is a solution of this, and every solution satisfies this congruence. Let's just check. (23 minus 5 is 18, is 6 times 3. So 23 is congruent to 5 mod 6. And 23 minus 8 is 15, is 15 times 1. So 23 is also congruent to 8 mod 15. So 23 is a solution. And every solution is 23 mod 30. For example, minus 7 is a solution. Minus 7 minus 5 is minus 12, is divisible by 6. Minus 7 minus 8 is minus 15, divisible by 15. Here, it's a problem to work on. Solve x congruent to 1 mod 3 and x congruent to 2 mod 4. Find all solutions. So spend a couple minutes working it out. Anyone find a solution? We know that the GCD of 3 and 4 is 1, so there has to be a solution. Solutions exist. And the least common multiple of 3 and 4 is 12. So the solutions are unique modulo 12. It'll be a whole congruence class modulo 12. So there's a quick way to find the solution when these numbers are so small. If a number is 2 mod 4, that means it's like 2, 6, 10, 14. So try 2. Does 2 work? 2 satisfies this, but not this. 6 doesn't satisfy this. 10 minus 2 is 8, is divisible by 4. 10 minus 1 is 9, is divisible by 3. So the quick way gives that a solution is x equal 10 plus any multiple of 12. So the congruence class of solutions is everything that's 10 mod 12. For example, 10 plus 7 times 12. What's 7 times 12? 10 plus 84 is 94. 94 has to work. Why? 94 minus 1 is 93, is 3 times 31, so 94 is congruent to 1 mod 3. 94 minus, let's see, 94 minus 2 is 92, is 4 times 23. So it's divisible by 4. So 94 is also a solution. Or 10 plus minus 3 times 12 is 10 minus 36 is minus 26. Is that a solution? Well, minus 26 minus 1 is minus 27, is 3 times minus 9, so that works. And minus 26 minus 2 is minus 28, is 4 times minus 7. So that's also a solution. Any number that's congruent to 10 mod 12 will be a solution. And that was like, I got this quickly just by testing some small numbers. But if I couldn't figure out how to do it that way, there's one method that always works. So this is using our sort of algorithm or method, if you like. If x is congruent to 1 mod 3, then x is 1 plus 3y. And if that's congruent to 2 mod 4, then 3y is congruent to 1 mod 4. So 3y has to be 1 plus 4, let's say z. I need to find a solution of this. I already did, actually. I can take z equal to minus 1, y equal minus 1. And if y is minus 1, 1 plus 3y is 1 minus 3 is minus 2. So any x equal to minus 2 plus a multiple of z. Now you might say, I found the solution as the congruence class of 10, and now the solution is the congruence class of minus 2, but of course they're the same. The congruence class of 10 mod 12 is the congruence class of 2 mod 12, because 10 is congruent to minus 2 mod 12. All right, well, this is not very theoretical. This is just doing a lot of calculations, which are fun. Good. Any questions about this? Oh, I should say on Wednesday, we'll only meet from 9 to 10. I have to leave at 10 o'clock on Wednesday morning. So on Wednesday, we'll have a short class. And I will also, after I email out a review session, I'll make sure that there are, in addition to class on Monday, several extra hours on Zoom where you can log on and ask me any questions you might have about anything we've done since the beginning of the semester. because we have covered a lot of material. It's very good, I think. Okay, any questions? Okay, if not, we will quit for the day. And I thank you all. See you on Wednesday.
Thank you, Professor.
Thank you.
Have a good one.
Thank you, Professor.
Thank you.
Thank you, Professor. Bye.